And the last paper, well, the presentation of this session is by Negin Golrezaei, and the topic is Learning Product Rankings, Robust to Fake Users. And she's with MIT, the Sloan School of Management, and she's a faculty member there in operations management. And she had her BS and MS in electrical engineering from Sharif University of Technology in Iran, and the Ph.D. from USC, where she received also a Ph.D. thesis award. And she has received several awards, actually, over the years, the Google Faculty Research Award and this Dantzig Dissertation Award, which I mentioned, the Informs Revenue Management and Pricing Section Dissertation Prize, and the Elwood Buffa Doctoral Dissertation Award. So the dissertation actually won several awards, so that's congratulations. And also the Ph.D. Achievement Award from USC. Her current research interests are in the areas of machine learning, statistical learning theory, mechanism design, and optimization algorithms, with applications to revenue management, pricing, and online markets. Negin?
Okay, so thank you very much for the generous introduction, and hello everyone. Hello everyone. Thank you for attending the talk. I also would like to thank the organizer for inviting me. It's a great pleasure to be here and have the opportunity of sharing some of my research with you. Two of my PhD students are actually here, Chinny and Jerry. They're going to have poster presentation later today, so we would love if you drop by their posters and let us know if you have any feedback. So today, I'm going to talk about how platforms can learn to do product ranking in the presence of fake users. So I'm going to only talk about one particular paper, but I want to also say that this paper is part of a broad research agenda that I'm following. And during this research agenda, we want to see how online marketplaces can use data to make better decisions when the data cannot be fully trusted. So here's a setting that you can see that why data cannot be fully trusted. And here we are providing a solution for the online marketplaces to still use their data, even if they cannot fully trust their data. And this is a joint work with my great quarters, Vahid Manshadi from Yale, John Schneider from Google, and Sheria Sekar from University of Toronto. And please feel free to stop me at any point if you have any questions. Okay, so for a minute, I want you to put yourself in the shoes of a seller on Amazon. And I want you to think about what would be the first thing that you would be concerned about, okay? So, and I want to argue that perhaps the first thing that you would be concerned about is going to be the competition on this platform. Because if you, for example, search for women's slippers, you will see there are more than 43,000 competitors in this market that are arranged over 400 pages. And then on top of that, there's another piece of bad news, because there are evidence that most of the users that might be interested in your product don't even go bother to the second page of search result, yet alone going to the page 400. So then I would say, as a seller on Amazon, perhaps you are really concerned about how Amazon is actually treating your product, and in particular, in what position Amazon is going to display your product. And in fact, product ranking is not only important for the sellers on Amazon, it's also important for platforms themselves, and because of the same reason. And that reason is position bias. And which is a fancy way of saying customers tend to examine the products that are more visible to them, and they appear in the top positions. Because of this position bias, now you can think about product ranking as a very important lever that is going to shape the demand for the customers, is going to help the platforms to maximize their revenue, like customer engagement or whatever other objective they might have. And in fact, many platforms try to take advantage of this level. And what they do is that they get engaged in something like that, I'm going to call it real-time learning. And every time a customer comes in, they try to show customers a list of products. They collect data in this loop, and then they update the algorithm, and this procedure will continue. Now, and usually at a very high level, the platforms try to do ranking, some popularity-based ranking. So they try to kind of estimate the popularity of the products, and based on that, come up with the right ranking for their platform. Now let's again go back to the sellers. So we know that sellers face severe competition. We know that they're kind of really desperate to get visibility they want for their products. And in particular, I want to say that on online platforms, there's some race for visibility. And this race for visibility is going to motivate many of the sellers on this platform to actually manipulate the algorithms by kind of creating fake data points in that inner loop that you'll see. And they do that in the hope that they get like really good position on this platform. Now, these like fraudulent activities and this manipulation are actually real. So there are a lot of evidence out there. So for example, here's an article from Wall Street Journal talking about like sellers on Amazon. They really try to trick Amazon to boost their sales. There are also other evidence. So then many sellers do such a thing, not only on Amazon, but on various platforms. Yes?
So wasn't this the same thing that came up with Google searches, and then Kleinberg's hubs and authorities sort of took care of it?
Yeah, yeah, at a very high level, that's also related.
Is there something like hubs and authorities that can happen here?
We are gonna like, yeah, so maybe when you have such problems or different things that you can do, maybe you can try to detect such fraudulent activities and maybe like take legal actions. But this is not the approach we are taking here. Yeah, so this is, I think like because we are saying no matter what kind of detection algorithm you do or like what kind of legal action you are taking, there might still like some fraudulent data points in your system. How can you be robust to such like fraudulent data points? So we are taking a slightly different approach, but that was. Oh, no. But I'll show you the model. And okay, sure. So, and the reason that we are saying, OK, we are not going to do the detection, we say, OK, fake user and these bots become like very sophisticated. It's become very hard to detect them. So then based on that, what if we really try to design data-driven learning algorithms that can identify optimal product ranking from customer click data despite the existence of this fraudulent activity and existence of these fake users. So that's the approach we are taking. And this problem is challenging because the number and identity of the fake users are usually not known in advance. In many cases, we don't know who is fake, who is not fake. And that's why this is not a trivial problem to address. Any question about the motivation? Okay. Now, here's the model. So to kind of look at this, to design like a good algorithm, we look at the simplest model that has this position effect and position bias effect within that. And that model is called cascade model. So for those of you who know about like auction design and like position auction, this is like one of the very popular model in that framework. The way it works is that if I have a real customer, and I show this like product I in position 1 to this customer, product J in position 2, product K in position 3, etc. First, customers try to examine the product which is placed in position 1, clicks on that with probability μi. If the clicks happen, the customer is happy, leaves the platform. If the click does not happen, the customer may actually exit the platform with certain probability. And with 1 minus probability, the customer is going to go back and examine the product in the second position. And this process will continue. And you can see that position bias exists because even if I put the same product, similar products in these two, for example, first position, the chance that the product in the first position is being examined is, like in that case, is 1. But the chance that the product in the second position is examined is much smaller. That depends on what happened to the earlier positions and also the exit probabilities. So this is what real customers do. Now let's think about like fake user, and that's related to the Vijay's question. Am I like taking the kind of game theoretic perspective? And the answer is no. So we assume that there are like T customers, F of them are fake. Fake user can do anything. They can like click on any products they want to boost the position of that particular product, future position of that product. Or they may avoid clicks altogether to downplay certain products. And you may wonder, why am I just making it too general? So first of all, making it too general is kind of would allow me to come up with a stronger framework that I'm robust against any particular strategy. But on top of that, like when we did like literature review, especially in the marketing literature, so there's some evidence that high quality sellers create these fraudulent data points, and for them it's because like these fake clicks are like a cherry on top. It's like a cheap advertisement. And there are also low quality sellers that they try to get engaged in some fraudulent activities, and for them it's because they really want to get like minimum level of visibility because their quality level is not really that high. So both type of seller can engage in this type of activities. And now let me reiterate that the platform cannot really distinguish between real and fake user, and despite that, it wants to do well and learn the optimal rank. Okay. So now, what's the platform problem? So the platform wants to maximize probability that the customer clicks on a product, which is also known as customer engagement. So we can also consider other type of like objective, revenue, for example. But I believe that this like simpler objective is allow me to kind of talk about the main idea behind making the algorithm robust. And then one thing is important is that the platform does not know click and exit probabilities in advance. But the platform really wants to learn this optimal ranking pi star, where in the optimal ranking, you would just go ahead with putting the best product, the one with the highest click probability in the top position, the second best product in the second position, etc. And now the platform would like, without having any knowledge, and only based on the previous observation, wants to minimize its regret, where the regret across T round would be the difference between the customer engagement across T rounds on their optimal ranking and the customer engagement on their like pi T across all the T rounds. So in an ideal world, I want the regret to be sublinear in T, because if that's sublinear, the per round regret would go to 0 as T, the number of customers, goes to infinity, and that means that eventually the algorithm actually learns the optimal ranking pi star. And this is where we are headed. And then we consider two different settings. The first setting is a simpler setting, is a fake-aware setting, where the platform is aware of the total number of fake user F. That's a good setting when the platform has like a rough idea or good like upper bound for the number of fake user, because as long as we have an upper bound, that our framework still works. The second setting is more challenging, is fake oblivious setting, so we don't even know the number of fake user. And despite that, we want to make sure that we do well. And the reason we focus on the first setting, which is kind of maybe not that practical, is that the idea over there helps us to design something, some nice algorithm for the second setting, which is more challenging. Any question about the model before I move on? Okay.
You don't differentiate between fake users and irrational. I mean, fake, I think, are intentionally are trying to mess up the system.
Yeah.
But
so
irrational ones, maybe their behavior is not aligned.
That's a very good question. I think here we are saying I want to be robust to fake user, but sometimes customers could be irrational. So maybe their behavior is kind of an outlier. So it doesn't match the patterns that we observe from like a regular customer. So this framework also allows us to be robust to those type of user as well. So if I, for example, have a user who wants to even like check every single page of like search results on Amazon, so this framework kind of like ignore such a user and still try to do well with respect to like a general user on the platform. But great question. So, yes.
In practice, what percentage of users are like not, I mean, they tend to abandon stuff or like
Okay, so I cannot give you a number, but I can for sure say that so in this work, for the theoretical result, I want F to be sublinear in T. But even if you increase T, like in the numerical study, we show that the framework works. Another thing that I want to say is that like if you, for example, look at platforms like Amazon, they are aware of that, And then one thing that they try to do to get rid of this like fraudulent user is that when it comes to calculating the average review score, they just focus on the newer data, and they get rid of the older data. Maybe that they do that because they are worried that some of the older data are already being manipulated. So they also do that. But I cannot give you like a number, say what percentage. That's a good question. Okay, so here's our main contribution. We studied this product ranking problem in the presence of fake user. We show that these traditional learning algorithms are not really robust to fake users. They get like linear regret. And then based on that, we designed two algorithms. One, we call it like fake over ranking for. So we had a little bit of fun with naming the algorithms. And then this algorithm gets a regret in the order of n square f times this logarithmic factor. And this additive factor is unavoidable because if you have, for example, if every like data points that you get is like coming from fake user, you cannot learn anything. That's why that pretty much there is a like additive factor proportional to f here. And this logarithmic factor is also unavoidable. So for those of you who know about like bandit literature, you would get like a similar term in the vanilla bandit as well. So then let me not talk about the ideas here for this algorithm and just say that we also designed another algorithm, fake oblivious ranking with cross-learning, that gets a regret in the order of n square f times this logarithmic factor. That's worse than what we get for far, which is expected because the setting is more challenging. But interestingly, when we did numerical studies, we observed that actually fork outperforms the far algorithm. And later towards the end of the talk, I'm going to make a remark why we think that this is the case and why like the numerical studies were not really confirming this bond. Of course, these are like upper bound, but nonetheless, we saw that forks are performing better than far. Yes?
So in the cascading bandits literature, often I've seen regret bounds in terms of two parameters. One is the total number of products. The other one is the number you can display at any one time.
Oh.
Here, what do you assume about, are they both n or?
Oh, okay, so here I'm assuming that if I have n products, I'm going to list them anyway. So maybe they go to the second page, third page, and maybe like there's exit probability that some customer don't even go bother seeing them. But yeah, but every product is being displayed. Okay, so let me also quickly review some of the related works. So there are two main literature that kind of our works is related to. One is like learning with corrupted data. This is more of like a recent literature, and it's started with this work by Licorice et al. Todoris, who is actually my colleague at MIT. So over there, they say, okay, let's say I have like a vanilla bandit, and then that follows like some stochastic vanilla bandit, and some of the like rewards that I'm getting are kind of corrupted. They don't really follow this stochastic like assumption that we impose. How can I still learn despite this corrupted data? So the reason that we cannot really directly apply such like algorithm to our setting is that first of all we are dealing with product ranking problem, which has this combinatorial aspect to that. So that's the one reason. Another thing is that fake user in our setting like make things more complicated. Because for example, if I have a fake user who clicks on a particular product that appears in position 5, not only this fake user is messing up the feedback I'm getting for that particular product, it's also messing up the feedback I'm getting for the other 4 products that appeared earlier, like in the first 4 position. So these are like, at a very high level, these are the 2 reasons that kind of existing works cannot be applied to our setting. So there are also works on learning with non-stationary environment when you have like changes in environment, but again, you cannot apply such setting to the algorithm over there to our setting. And there are also like some papers that they look at incentive-aware learning, which I also have like some works in that area. So over there, the problem is different. Maybe like we would take the game theoretic aspect. So because we would say, how can I, like let's say there is a other player that is giving me this data. In this incentive-aware learning, I'm asking myself, how can I push the other player to give me clean data? How can I incentivize the other player to actually give me clean data to work with? In this work, we are not really pushing the fake user to give us clean data. They can do whatever they want. But regardless what they do, I want to achieve robustness. And finally, there is this literature on product ranking, mainly in the OMOR literature. This problem has been studied in the offline setting and also online setting. So in the afternoon, Rod is going to actually talk about another work that at the high level kind of contributes to this online learning for product ranking. So what's the punchline? So we are the first work that look at this product ranking problem when the data are being corrupted. And given the combinatorial nature of the problem and the harm that the fake user can cause to the system, we cannot use the existing algorithms for this setting. Okay, so let's now get to the more exciting part of the talk, because I want to first argue that if you go with traditional learning algorithms, they're going to fail. They're not going to be robust. And for example, if you go with UCP-based type algorithm, there are instances under which this type of algorithm gets linear regret. And these instances are quite simple. So suppose that you have two products, and then fake user arrive first to manipulate things at the beginning. And then this fake user inflate the click probability of the worst product and try to deflate the click probability of the better product. So if they do that only for log t square run, so after that period, the UCP algorithm wrongfully thinks that the better product is the worst product and vice versa. And it actually never recovers from this wrong belief. And as a result, it gets a linear regret. So UCP is not working. So let's see what is going to work here. Okay. So to answer that question, we first go to the first setting, which was an easier setting to study. And there, the number of fake users is known. Okay. Now, the algorithm that we come up with take advantage of two main ideas. So the first idea is being conservative, because the algorithm knows that not every data point it gets is actually coming from real customers. So it's going to take the data with a grain of salt. And in particular, when it's tries to estimate the click probability of the products, and it's tries to form a confidence interval around it, it tries to widen the confidence interval. Okay? And it widens the interval by a factor, additive factor, which is proportional to f. Recall that the algorithm knows f. So that's the first idea, being conservative. Then the second idea is related to this combinatorial challenge of the product ranking, because we don't want to experiment with every single ranking when we try to learn the best ranking over products. So then what the algorithm does is maintain a pairwise product relationship graph. And then in this graph, so you are going to have node for every product. And then at the beginning, this graph is empty, no edges. And as I'm getting data, I'm just going to add edges to this graph. And for example, if I see here that the lower confidence of product J is greater than the higher confidence bound of product I, I'm just going to go ahead and add a product link between I and J, just to say that we believe that J is better than I, despite the fact that some of the data are being corrupted. Okay, so then putting these two ideas, this in every run T, rank pi T is going to be simply a topological order over this pairwise graph, because this graph may not have may only contain some partial order over the products, but nonetheless we go with topological ordering of the pairwise graph with some careful tie breaking. And then we show that by following this idea, for algorithm is going to get regret in the order of n square f, and this logarithmic factor. And as I said, this is not avoidable. This is also not this cannot be avoided as well. Yeah, I think if you remember pi star, the optimal ranking, in the optimal ranking we would go with the mu, the highest mu in for the first position, and yeah, and that's why this product relationship graph is going to guide us how to do the ranking. Yes.
So how highly is it dependent on?
Oh yeah, that's a very good question. I think we don't know whether this is the n squared is required, and I think perhaps it can be removed, but we will not be able to remove that in the regret one. But that's a good question. Yeah, I think if you believe that customers can see all the products in the first page, first of all, we can put the exit probability of all the position to be 0 for the first K position, all the ones that are in the first page, and then make the exit probability of the one in the last kind of equal to 1, meaning that nobody is going to pass that. So yeah, so kind of you can still use this methodology for assortment planning type of problem rather than the product ranking as well. But that's a very good question. Ozan, yes.
So because of the delta Ji in the denominator,
yeah.
Give out the loss term as almost
Yeah, because you have summation over J and I, and then yeah, this should be also scales with n square as well. Yeah.
Sorry, can I come back to your
Sure.
400 pages of Amazon?
Yeah, sure.
Can't Amazon just randomize those 400 pages for each customer? Randomly produce a different order for each customer?
So if they do that, so in some cases, the customer may suffer a lot. So they may see like very random stuff. Yeah.
That's the idea.
Yeah.
I mean, why should they all see the first page only? Somebody should see the 30th page, somebody should see the 400th page.
So I think that's a very excellent question. We have like a different paper in which we are trying to kind of be fair to sellers. And in a sense that, okay, I don't want really give like bad visibility to particular seller if this like is quality is as good as like other products. And we show that randomization is actually key there. And you don't need to actually randomize over like too many sets. It's enough to randomize over n squared number of sets. And when you do that, also like the price of like fairness, we characterize it is not like that much. So it's kind of.
It doesn't have to be uniformly random.
No, it shouldn't be. Yeah, exactly. So we have like a kind of algorithmic way of like making kind of do randomization over sets, and then by doing that, we make sure that sellers we are being fair to sellers in terms of visibility. At the same time, we are not doing too much of randomization, and customers also don't suffer by seeing completely random stuff. But that's a great question. Okay, so so quickly talk about the proof sketch. The first step is decomposing the regret into multiple like terms, where every term is going to be associated with the loss coming from misplacing an inferior product to for a given position J. Step 2 is that we show that because of being conservative, the added edges in the graph are going to be accurate with high probability. And in step 3, we provide an upper bound on the number of times we make a mistake by putting an inferior product in a better position. So putting all these steps together, we get the regret bound that I presented. So now let's get to the more challenging setting. So because for many platforms, perhaps we are in this setting where the number of fake users is not even known to the platform. And if I want to look at this setting at a very high level, I still want to be conservative, right? Being conservative is helpful here because not every data point can be trusted. So I want to take the data with kind of grain of salt. But if I want to be conservative, I need to enlarge the confidence interval, but I don't know if. Okay, so I don't know by how much I need to enlarge the confidence interval. That's the main challenge. So the way we overcome this challenge is based on two main ideas. So the first idea is that I'm going to create multiple algorithms that are going to target different conservatism levels. Because I don't know what's the right level of conservatism level. So I'm going to create multiple levels in order to target different conservatism levels. And then the second idea is that at least for some of the levels, I'm going to artificially limit the number of fake users they see. And I'm going to use that artificial number to kind of enlarge the confidence interval. These are the two ideas. Okay. So idea 1, this is about targeting different conservatism level. So for that one, I'm going to keep multiple copies of the 4 algorithms, meaning that each of these 4 algorithms are going to have their own confidence interval, their own graph. But when let me not tell you by how much I'm going to widen the confidence interval yet. But there's some widening of the confidence interval happening. So I'm going to have 4 in level 1, level 2, up to level L, which is log T. So every time when I want to make a decision, I'm going to choose one of these levels at random and follow the recommendation of that particular algorithm. Okay. So what am I trying to achieve here? Because if there are the same copy of the 4 algorithm, why having multiple levels is even helping? So what am I trying to achieve here is that I want to make sure that these algorithms target different conservatism level. And to do that, I'm going to choose them with different probabilities. So with probability half, I'm going to go with the 4 in level 1. With probability 1/4, I'm going to go with level 2. Up to here with probability 1/2 to the power of L, I'm just going to go with the last level. And now, as I'm going from this level 1 to level L, these levels see less corrupted data points because I don't really actually passing any data points to them. I actually use them with a very small probability. So they also see very few corrupted data points, which is really good. They're going to be slow learners, but they're also going to be more conservative. Okay? And that's like having different probabilities allows me to have like different conservatism level in a very implicit way. Now, what's the second idea? The second idea is about artificially limiting the number of fake users at least for some of the levels. And that's based on this like simple lemma that says for any level greater than L star log F, these levels are not going to see more than log T number of fake users. Okay? So, and that's because like I don't really invoke these levels with high probability. So as a result, at most these levels are going to see log T fake users. So then why this is helpful? This is helpful because now in all of these for algorithm, I'm going to use that log T to enlarge the confidence interval. And at least I know if I do that for these higher levels, this is the right level of conservatism. And if I do that by the proof of the for algorithm, I know that whatever decision these levels make for adding edges, they're going to be correct edges. Okay. So that's take care of these higher levels, making sure that they don't make a lot of mistakes in terms they don't make it with high probability, they don't make mistakes. But there are still two main questions. First thing is that, okay, so now you tell me that high levels are okay because when it comes to widening the confidence interval, you use the right factor. But what about these low levels? Because most of the time you are actually invoking them. With higher probability, you are invoking them. So how can I make sure that these lower levels also learn the correct edges? That's the first question. The second question is that, okay, higher levels, I know they don't see a lot of corrupted data points, and then we did the right amount of like enlarging the confidence interval for them, but they can be really slow. Maybe most of the time their graph is empty. So then in that case, they are not helping as much. How can I make sure that they learn the correct edges fast enough so they can pass these correct edges to the lower level as soon as possible? Okay, and the answer to both of these questions is bi-directional cross-learning idea. So the first idea is downward cross-learning. So any edges that I have at level L, I'm going to transfer it to the lower levels, 1 to L minus 1. So here's an example. I know that level 2 is more conservative than level 1. And suppose that this level 2 end up adding an edge between like product I and J. I'm just going to literally transfer this edge to level 1 as well. And that's by doing that, I make sure that these lower levels also learn the correct edges. The second idea is upward cross-learning, which was actually a novel aspect of the design, and that helped us to get the regret we wanted. So that upward cross-learning is about related to the second question, because in the second question, we were worried about the higher levels learn things at a very slow rate. So in upward cross-learning, when we get samples at this level 1 to L minus 1, we somehow transfer them to the level L with some factor. We are not going to transfer all of them, but with some factor, we do transform them. And that's the way that you can visualize it. So based on these two ideas, we managed to answer these two questions that I raised earlier on. And that leads us to this theorem that the fork algorithm incurs regret in the order of n squared f times this logarithmic factor. So let me pause here to see if there are any questions. Yes?
Upward learning, when you're just transferring the samples, why can't you just use all the samples? Like the samples are agnostic to what you assumed about the generation of the samples. Why can't you use all the samples?
So if I use the sample, it's also possible that all these higher levels see all the, for example, even up to F number of fake users. But then if that happens, I cannot really say that high levels make the decision with right decision with the high probability. Because if you remember, I needed to enlarge the confidence interval for this for these levels. I did not know F, but at least I knew that these high levels are going to see at most this log T fake user in average. So then for these levels, if I go and enlarge the confidence interval by this factor, theoretically I can say that any level greater than L star, they are going to make the right decision when it comes to adding the edges in the graph. But if I transfer all the samples to them, that would I can kind of would corrupt these higher levels, so then I can no longer say that these are making correct edges with high probability. Yes.
So how do you
No, there are like parallel algorithms. They are there, and then kind of every time I flip a coin, I do like, and I choose like one of these algorithm, one of these levels with some probability. And they're kind of evolving on their own. The only way that these levels communicate with each other is through this downward cross-learning and upward cross-learning. But think about it as like a parallel copy of like the same FAR algorithm, with the difference of their confidence interval is not being enlarged by the factor proportional to f, but is being enlarged by factor proportional to log t. Yes? Yeah, I think like when we first started working on this problem, I thought like maybe this is related to mean being more robust to median, median being more robust than mean. So then we actually started to think about like what if I try to, instead of estimating the kind of the click probability, try to learn the median, it didn't help as much. I'm not saying we took that route, it didn't help us in the design, but yeah, that there is connection. Yes. Yeah, exactly. So I like, for example, think about this level L star. This level is being like chosen with probability 1 over f. And if there are even at most f number of HQs, there kind of in expectation, this level is supposed to see constant number, or even like in the worst case, log t if you go with the concentration inequalities. So they're like being invoked with a small probability. And then as a result, they don't see a lot of corrupted data. So they could be slow. That's why upward cross-learning was quite essential for us to kind of speed them up.
Is there a fast, quick way to see the log? Probability is 1 over f.
Yeah, even like for this one is like 1 over f times f would be constant. So then it's kind of, if you want to kind of have an extra buffer for the concentration inequality to go through, you need an extra log t factor. Okay. And then, so after the design, we asked ourselves, okay, let's actually do some simulation to see how these algorithms perform. So we compare UCB with FAR and fork. UCB in a more generalized instances, not even the stylized example that I talk about for the proof of our result, it gets linear regret. It's not really robust. By the way, this is regret, so the lower the better. So, and this is a FAR algorithm, regret of FAR. This is the regret of fork algorithm. And to our surprise, we observed that fork is doing much better than FAR. The reason that we think is what's happening, like we observed this, is that maybe FAR, because we wanted to get the theoretical result, we enlarged the confidence interval for that algorithm by too much. Ended up like being too conservative and quite not decisive. So if the confidence interval is like way too large, so the algorithm is not making any decision for a long time. But fork algorithm does not have that. It's kind of, and maybe without knowing if, it hits the right level of conservatism and even like manages to do well and outperform the FAR algorithm, which is, I think, is a good news, because in most cases we are going to be in that scenario, right? So now we say that as a platform, we don't need to go and estimate f or have a good upper bound for f. Just run this fork algorithm, which is like fake oblivious, and then you are going to get good result. So we also like try to understand the impact of this upward cross-learning. Because upward cross-learning was kind of the novel aspect of the design and help us to show the regret. So here I compare fork with like 4 minus, which is the fork with downward cross-learning but no upward cross-learning. And we observe that even in the simulation, it's having upward cross-learning is going to give an edge to the algorithm, and it's going to reduce the regret. So we were not able to manage to show that 4 minus is going to get a linear regret, or like theoretically show that 4 minus is worse than 4. But nonetheless, the numerical result shows that upward cross-learning is quite essential here. OK, so let me summarize. So in this work, kind of motivated by the fact that many online platforms want to make decisions using their data and use machine learning algorithms. We look at product ranking problems in the presence of fake users. We show that if you go with traditional learning algorithms like UCB, those algorithms tend to be quite fragile and they can be easily tricked. So then we designed two learning algorithms. One is going to be FAR, which widen the confidence interval and use this pairwise relationship graph to make decisions. And then the second one was Fork, that leverage this multi-level learning algorithm and this bi-directional cross-learning between different levels. So I did not talk about, but we also have this result that says, okay, what if I make sure that fake users are not really bursty, but they are spread out? Because in many cases, these fake users are being hired by someone to kind of create these fake clicks, and maybe they have limited budget that they try to spread over time. For that one, we show that the same algorithms can do much better if the fake users are kind of spread out. And at a very high level, I think hopefully this work can be used for various other settings when you have spam reviews or fake likes or even fake purchases, and maybe being conservative. It's going to be helpful in other settings and parallelization and randomization as well. So with that, I'm just going to wrap up the talk. Thank you so much for listening to my talk, and I will take any question that you might have. Thank you. Yes.
Is fake or not? You get some, but maybe the prediction itself could be fake, wrong.
So I think that's a very good question. We have an ongoing work in which we try to combine detection with learning. So because let's say you have a detection algorithm, and detection algorithm would give you a score, how confident the algorithm is about this user being fake or not. This is an ongoing work. I don't know. We are really hoping that we can kind of, by leveraging detection, by combining these two, we can achieve better result. But that's a very good question.
Sometimes when you're looking for a product, they throw in things which are kind of related, but not along that line. In other words, to attract the attention, maybe the user does not know exactly what they want, or they might be interested in something else, and then you throw that in, and then it may attract attention, and they'll click on it and buy it, even though that was not their intention. Is there anything of that sort that can be accommodated?
I think not in this one, but I have another paper on product ranking, and over there actually we say the same thing. So sometimes user may not really know what they are looking for, and in that case maybe even going with this kind of score-based or popularity-based ranking may not be the optimal thing, because maybe you want to throw something within in the top position in order for the user to see, and maybe that's become the favorite item for that particular user. And we have the result that under some setting, this popularity-based ranking may not be optimal even for the user themselves. Maybe there's a way to kind of combine that result for this one to make it also robust, but that's a very good question.
Thank you.
So I just heard a talk a couple of weeks ago by somebody from Amazon. I think they have two pieces of information about clicking. One is whether somebody clicks on the product, and the second thing is whether they follow up and buy the product. So these two are correlated, but they have two pieces of information. I would assume that fake users would not be buying the product, they'd probably just click on it. So I wonder if that could be helpful in sort of figuring out who is fake, whether that can reduce the regret.
So I actually have thought about that. So in many cases, you have more than one signal. This is why I use clicks, but sometimes you may have also fake reviews or fake purchases. And actually, fake purchases are real. So especially if the Amazon does not fulfill the order, so someone would click that I purchased, and kind of nothing will be shipped, but then that imaginary, this user also end up writing a fake review on that. But nonetheless, creating fake purchases is more costly than creating fake clicks. Fake clicks is a very cheap thing to do. And then maybe one idea is that how can I combine various signals that the cost of manipulation are kind of heterogeneous. Some are more costly than others, but they still be robust. I can believe that in such a case, maybe using the signals that are less costlier would be helpful, but such a signal is also sparse, right? So maybe you get a lot of click data, but not a lot of purchase data. So that's why maybe it's better to combine them rather than only relying on the purchase data, which is not going to be sparse enough. But yeah, this is a direction that could be like interesting for future. Yeah, thank you.
Any other questions? Yes,
So if you were to subsample the history, so if f is small relative to t, if I were to just subsample and discard some of the data points over time, and then use something like UCB, would that also help in reducing the regret?
So if really a small, okay. So you're saying if it's a small and then I kind of remove the data at the beginning and then...
Not at the beginning, randomly sample.
Randomly sample the data. Randomly sample the data and then throw away the rest of the data?
I mean, just the idea is to basically remove, use a subset of the data with the hopes that over time the weight of the non-fake reviews is going to be higher.
I don't know if this algorithm would give you the regret that you want, but at the very high level, randomization is usually like the way to go. Also, in that design, we had this randomization over levels that allow us to kind of get the regret we want. But maybe for your randomization to work out, you need to know F, because you would know that without that, maybe it's not very clear how to do that.
Thank you very much.
Thank you so much. Thank you.